Welcome student, in this video we will see the state reduction and state assignment. So it avoids the introduction of redundant state. Repeated state can be avoided. Redundant state reduce the number of flip-flop logic gate, reducing the cost of the final circuit, right? So while going with the state diagram, then that reduction of the state diagram and state assignment, we can repeated states can be avoided, so that we can reduce the number of flip-flop, number of logic gates, so that the cost of the final circuit can be reduced, right? Now we'll see the what is the state reduction. When two states are equivalent, one of them can be removed without altering the input and output relationship. That is called a state reduction, right? When the two states are equivalent, we can remove one of the state without altering the input and output, right? Now we'll see the one state diagram. From that we can go for state reduction. So this is the state diagram. The corresponding state table is available, right? This is the present state. This is the next state when input is x equal to 0, next state when input x equal to 1. This is the output. When x equal to 0, this is the output. When x equal to 1, this is the output, right? So the states are indicated by the circle. So these directed lines, the state from one state to another state. This 0, 0 indicates input and output, right? So we can see this state diagram by relating with the state table. First we will take the A goes to B. If x equal to 0, input is 0, output also 0. A goes to B, input is 0, output also 0. A goes to D, when x equal to 1, output is 1, right? A goes to D, when input is 1, the output also 1, right? Then we will go to B. B goes to F, when x equal to input is 1, output also 1, right? So B goes to F, when input x equal to 1, output also 1. Then B goes to E, when input is 0, output also 0. B goes to E, when input is 0, then output also 0, right? Then we'll go to F. We'll go in this order, right? F goes to C, when input is 1, output is 0, right? See this, F goes to C, when input is 1, output is 0, right? F goes to C for input 1, but the output is 0. F goes to F itself, for x equal to 0, input is 0, output also 0. F goes to F, for input equal to 0 and output also 0. Now we'll go to the E. The E goes to F, when input is 1, output also 1, right? This is E. E goes to F, when input is 1, output also 1, right? E goes to E itself, for input and output is 0. E goes to E itself, for input equal to 0, output also 0, right? Now we'll go to D. D goes to E, for input and output is 0. D goes to E, for input equal to 0, output also 0, right? D goes to B, for input and output is 1. D goes to B, for input is 1, output also 1, right? Now this is completed. Now we'll go to C, right? C goes to D, for input and output is 1. C goes to D, for input equal to 1, output also 1, right? Another thing, C goes to B, for input output is 0, 0. C goes to B. So C goes to B, when input is 0, then output also 0, right? So this is the state diagram, the corresponding state table. We analyze the, from the state table, we analyze the state diagram, we analyze the state table. Now we need to analyze what are the repeated terms are available. So in this there are two repeated states available, indicated by this blue color, A, B, D, 0, 1. Similarly C, B, D, 0, 1, right? This first and third row are repeated. Similarly this red color, second and fifth row, B, E, F, 0, 1, E, E, F, 0, 1. So we can avoid these two terms are repeated, we can avoid any one, right? From A, B, D, 0, 1, C, B, D, 0, 1, we can avoid this C, B, D, 0, 1, right? So this C is now represented by the A, right? We are replacing this C with A, so that we can take only A, B, D, 0, 1, right? Similarly this red color lines, BEF01, EEF01. We can avoid this. We can eliminate this fifth line, right? So that this B, this E is now represented by B, right? While eliminating, we need to see how to represent, right? So while eliminating C, this row, the C is replaced by, used by A. Similarly, this E is replaced by, used by B, right? So that now we can eliminate this third row as well as the fifth row. So that is called a state reduction, right? So by analyzing the table, there are two repeated states available, first and third row, second and fifth row. So third row and fifth row is eliminated. The correspondingly C is used as A, E is used as B. Now we'll see the reduced state table, right? Here 1, 2, 3, 4, 5, 6 rows available. Now 2 rows are reduced, only we have 4 rows will be available. We'll go to the reduced state table. So this is the reduced state table. There are only 4 rows available. Second and fifth row is eliminated. So from this reduced table, we can draw the reduced state diagram. See this, now the state diagram is reduced, right? So A goes to B when input is 0, output also 0. A goes to B when input is 0, output also 0, right? A goes to D when input and output is 1. A goes to D when input is 1, output is 1. We will go to B. B goes to B itself when input and output are 0. B goes to B itself when input is 0, output also 0, right? B goes to F in input and output is 1. B goes to F when input is 1, output also 1, right? Now we'll go to D. D goes to B, right, when both input and output is 1, right? D goes to B when input is 0, output is also, both are same. D goes to B only for input and output is 0, for input output also 1, right? For x equal to 0 also output is 0, for x equal to 1 also output is 1, right? 0, 0, 0, 1, right? So D goes to B when input is 0, output is 0. D goes to B also when input is 1 and output also 1, right? Now all the states are covered. This F goes to A, everything. So this is the reduced state diagram, right? So 2 states are repeated, that is eliminated, so that we got 4 row. From that we can draw the reduced state diagram. Now we'll see the description. State assignment. The process of assignment binary value of the state of the sequential machine is known as the state assignment. We need to go for a sequential machine, is nothing but a state assignment. Then rules for state assignment. First one is states having the same next state for a given input condition should have assignment which can be grouped into logically adjacent cell in the K map, right? That is the first condition. Second one, states that are the next state of the single state should have the assignment which can be grouped into logically in the adjacent cell of the K map. So these are all the 2 rules in the state assignment. The separate problem available for state assignment, at that time you are able to know very well. Then transition of the output table. So it can be obtained from the state table by modifying the entries of the state table with the selected state assignment. Then excitation table. It gives information about the excitation to be applied to the flip flop to bring the machine from the present state to next state, right? The entire excitation table we can prepare, so that is applied to the flip flop, that is from present state to next state. So in this video we discuss about the state reduction and state assignment. We discuss one problem, right? We discuss the state table and state diagram. From that we got the reduced state diagram and state table, right? Thank you for listening.